last couple weeks, and it's interfering with my presentation abilities. Second, I've got information up here, my email address. I will also have it at the end, and you can get it from Jason or Darlene or Nancy. If after this you would like a free sample, I'm happy to send them. I also offer 1 hour of professional development training for any engineers in the audience who would like it. Just please let me know that you are here, and I can get the certificate out to you.
And David, let me jump in real quick.
Yes.
At the end of the presentation, I would also like to let everyone know that if you would like the special provision I wrote while at the Michigan Department of Transportation to use these in construction projects, please let me know and I can send it your way.
All right, thank you, Jason. All right, I wasn't sure exactly who the audience was, whether it's engineers or maintenance crews, so I've got a little bit for everybody. What I'd like to do first, though, is just go through a quick refresh about what it is we're talking about. Retaining walls, structures, drainage. Talk about some failure points. If there are any inspectors in the audience, what are the things you look for in a structure to know that there's a problem going on? Then talk about some innovations and project examples. So real quick, we're talking about retaining structures. And those can be any kind of structure, these that I'm showing, plus tunnels or anything that's holding up soils on one side. And whenever you design a structure, you've got the weight of the soil, and if you have a low water table, you don't have any extra pressure on the wall. When the water table goes up, the pressure goes up. The goal is to lower the pressure. So you always put in some drainage systems. This happens to be a weep hole, which is located, in this example, halfway down the wall, which means the pressure is lowering to halfway down the wall. So the goal is to get a drainage system as low on the wall as possible in order to keep the pressure as low as possible. Now, when I talk about drainage systems, I'm really talking about two components. One is the actual water or hydrostatic pressure coming off the wall through some sort of a weep hole, drains, could be coming through the seams and MSE and block walls. There are strip drains, wall drains, but anything that is getting the water off. The second component is soil filtration. And that is, while the water's coming off, how do you keep the soils and the backfill from coming out with the water? So traditionally, before the advent of geotextiles, that was done with a granular filtration system. So that could be a crushed stone, some sand, would be the backfill that would stop the native soils from passing out the drainage system. And they may have used some burlap or some bags of sand behind the wall to stop the soils and backfill from passing out. Then geotextiles came along, kind of changed the whole game. And geotextiles were then used for the soil filtration of the drainage system. But what really happens with soil filtration and geotextiles when they're put into the backfill? Geotextiles are designed, so in this example here, you can see the geotextile is flush up against a wall. Water's flowing from the left to the right. And as it flows, it brings soil fines or backfill material towards the wall. And that builds up on top of the geotextile. So the geotextile stops the largest particles, fills in with some more particles, and then fills in with the smallest particles. And that creates a filter cake or transition zone. It is basically a granular filtration component that is built up on top of the geotextile filter fabric. And that's where, that's the perfect situation, and that's what provides the drainage and stops other soil fines from passing through. But when you put a geotextile filter fabric into backfill, the drainage performance will start to decrease. So as this filter cake builds up, or as the geotextile becomes clogged, drainage performance decreases. And in a perfect world, you want it to get to a steady state. So it's not the same number that it says on the specifications of a geotextile. It's a lower flow rate because you've got soils and backfill mixed in there. And if you can maintain that steady state, that is great. The challenge is that over time, the geotextiles can become clogged. They can foul up, and when they do, they will stop allowing water to pass. And as the water stops, it builds up pressure, and then pressure, the water is going to find a way. It's either going to go around the clogged geotextile, or it's going to go through the geotextile, ripping holes in it, and then soil fines will pass out through the drainage outlet or through cracks in the wall, around the wall, under the wall. The soil is going to go out, and then that can lead to voids and sinkholes. So if you think about it, there's really two different phenomenon that foul up a geotextile. One is called clogging, which is generally the same term that's used for both situations, but they are distinct phenomenon. Clogging is when soil fines get trapped inside the geotextile, and as they get trapped and block the flow, more pressure builds up, pushing more soil fines into the geotextile, causing more clogging and decreased performance. The other phenomenon is called blinding. And if you take your hands and you rub them together, that is intimate contact. Geotextiles require intimate contact with backfills and soils in order to perform correctly. If there are any folds or creases or bends in the geotextile filter fabric, those will fill up with very small soil, soil fines, and those soil fines will turn into an impermeable slurry, and that slurry will spread across the geotextile. And that then stops water from passing through the geotextile. So over time, if you have existing structures with existing drainage systems, those drainage systems will, over time, start to decrease in performance and ultimately will foul up, and then you'll have other problems. Now, the real question is, well, how long does that take? And that could be as quick as a couple years. It could be 30 years before drainage system fails. And that is highly dependent on the local situation, local hydrology, how it was designed, what type of drainage system it was. But over time, performance will decrease. There are a lot of studies about geotextile flow rates, but not many actually use soils, different soils, and also create different cyclic environments, such as dehydrating the soil, rehydrating the soil, things that the soils are going to go through naturally out in the field. Well, this is a study here, came out a few years ago, with 3 geotextile filter fabrics. And over the course of this study, the performance of the geotextile filter fabric decreased between 70% to 85%. So now this was a laboratory, and they did different things, but over time, the geotextiles will start to foul up. Performance will decrease. So I mentioned a filter cake before, this transition zone, and if that can be established, then the structure can go for a long time without any problems. The challenge is that the transition zone, there are many things that disrupt the backfill and disrupt that. One of them is bidirectional water flow. So if you have a drainage outlet that is along a riverbank or anywhere that is going to have higher water levels, you've got water going into the drainage outlet, those will disrupt the backfill and cause a decrease in the performance faster than if it was just a land-based application. Another is road vibration. So if you have, you've got an abutment or maybe a culvert, and you've got cars going, along an approach, and they get to the bridge deck, and every time they go over that transition, there's little vibrations, especially when trucks go across. All those little vibrations will disrupt the backfill and cause the drainage performance to decrease. So especially with abutments, you've got massive structures, very strong structures, but water will build up quicker behind those structures over time as road vibration disrupts their drainage system. Biological clogging is a big one. If you've ever worked in high iron content soils, iron ochre is a byproduct of a bacteria that likes to eat iron. This is soluble. It's permeable when wet, but it's impermeable when it dries out and solidifies, and that can foul up a drainage system. Mineral clogging also fouls up drainage system. A man-made issue with drainage systems is mud jacking, injection grouting. If you need to do any kind of work like this, this will foul up whatever drainage system was behind the wall. It's a seawall example of the same phenomenon. And all of these can be solved. They just, it's a secondary consequence of trying to fix a primary problem. So if you're out inspecting walls, what are some things to look for? Well, signs of excessive moisture could be if you have a structure that has paint or stucco, it's not sticking. The wall is too moist. You can see moisture on the wall. Excessive efflorescence. This happens in new construction, new concrete, but if it's an existing structure and this is still happening, you've got water coming through the structure. Cracks on this happens to be a beam on a bridge abutment, pre-stressed concrete beam. Water was getting between inside the beam from behind the abutment and causing cracking along the beam. Change in vegetation. This is a box culvert, Michigan DOT, and you can see right in the center here, you can see distinct lines of where the vegetation changed right on top of the box culvert. Further back, the vegetation changed again. And looking at these plants, they were very high moisture loving content plants. Then they became a little bit more arid, and the further it got away from the wall, the more arid the plants were because water was pushing towards the structure, building up as closer it got to the structure. And on top of the structure, it was saturated soils for a very long time. Saturated soils are sinking in. The drainage system for the structure nearby is probably holding back a lot of moisture. If you see panels separate, if you see walls rotating, any kind of wall movement, especially on an existing structure, is probably caused by hydrostatic pressure buildup behind the wall. If you see drainage outlets where you've got soil coming out, then the soil filtration component has failed. If you have grasses or other vegetation growing out of a structure, those roots are damaging the soil filtration component, and soil fines will pass out through those gaps that are being created with the vegetation. If you see any kind of sinkholes forming, voids forming by collapsed, whether it's a depression or a sinkhole, the soil filtration component has failed and the soil's been washed out somewhere. Okay, so what do you do if you notice any of these signs? Typically it's very difficult to, the traditional way of fixing it would be to bring in a backhoe, rip up the structure, dig down, put in a new drainage system, and that's really not cost effective. You could try cleaning out the piping system, but that's extremely difficult and sometimes impossible to do. You can plug the drainage outlet so there's no more soil fines coming out, but that will then lead to further damage. You can excavate, but that's cost ineffective. You can put in new drainage outlets, but the challenge here is, well, fine, you let the water out, but now how do you stop the soils from coming out? So the question was, well, what if you could cost effectively fix a drainage system and extend the life of a structure? What if that drainage system was maintainable, so you never got into the position where it's failed and you've got damage on the wall? A solution that would provide faster drawdown and something that is easily inspectable so that an inspector just walking by can tell if it's working or not without having to touch it. So the idea for maintainable weep hole filters was born with those ideas. I'm going to try and turn on my video. I want to, hopefully it doesn't say I have to, hopefully you can see me now. So I am holding up what you see in the picture here. So this is what we call a maintainable weep hole filter. It is basically a 316L stainless steel housing with perforations in it. This installs into any existing or new weep hole. So it's installed here, fastened to the wall. Then inside is a geotextile filter cartridge that contains geotextile filter fabric. And this is the component that is intended to be removed, can be brushed off, can be reinserted to maintain drainage performance. Then on the front side, there's face plates that some have a backflow prevention valve on them.
Hey, David, did you hear me? Can you raise it up a little bit?
Yeah. Did you see everything, or do I need to start from the beginning?
No, I don't think you need to start over, but the faceplate.
Okay. So this just has a valve on it. Some come with a valve or don't need a valve. The valve is intended to stop that water pressure from entering into the drainage outlet. And then there are different sizes. So this is a smaller version, a little bit bigger. So these are used for different types of structures depending on the size of the structure. And then finally, there are very large units which provide significant drainage capacity. You can kind of see I'll hold these together. And they're used for very large structures or structures that have significant drainage requirements. So just real quick, a couple of the, I mentioned most of the benefits. Additionally, I mentioned the valve is used to block this storm surge and water, but it also stops mosquitoes from breeding in drainage outlets. And in some states, in some areas, that's a very big problem. You get a little bit of water left in the drainage outlet, and mosquitoes love to breed in there. So I mentioned faster drainage. Well, the conical shape of the unit, here you've got an image of a unit put into a weep hole with water flowing towards the conical shape, as opposed to a traditional weep hole that is just, we call it a two-dimensional weep hole. So it's a hole in the wall with a geotextile filter fabric flush up against the hole on the back side. Well, 4-inch hole, for example, has about 12 square inches of surface area on the geotextile filter fabric. The same 4-inch hole with a conical shape has 26 square inches of geotextile filter fabric. So why is that important? Well, the surface area of the geotextile filter fabric and the type of geotextile filter fabric plays a significant role in how fast water can pass out a drainage outlet. So backfill also plays a role. If you have a good permeable backfill, then the geotextile is actually controlling. If you have a high clay backfill, then the soil side is controlling. But the conical shape demonstrates a significant increase in the amount of water that can get out of a drainage outlet at any time. So the example of the 4-inch produces, the conical shape produces 192% greater flow. All right, so I'd like to just talk about installation and maintenance. I've got a video to show about installing. Installation can be very straightforward, and most times it's very simple. If you have an existing weep hole, the units can typically just slide into the weep hole and be mounted. However, if the weep hole is not producing water, there are some techniques to kind of break up the backfill to get it to produce water. If it's not producing water at all, or there are no weep holes, then it's as simple as coring a weep hole into the structure, putting the unit in, mounting it with the mounting fasteners that are provided. It all comes pre-assembled, and then it will start draining. Sometimes there's very poor backfill, so there are some other techniques to get some better permeable backfill. What you're seeing here is new construction, so this all looks good, but there are techniques to get stone into an existing structure to help the water flow if it's if the backfill is poor. So the real question then typically comes down to maintenance and frequency of maintenance. So a couple of things. The units are designed to be maintainable quickly and easily. If they ever need maintenance, it takes about 2 to 3 minutes. Of course, after you've done a few, that can be shorter. And simply, you pop out the cartridge, swish it in water, if available, brush it off with a soft bristle brush, put it back in, and you've restored drainage. Now, I get the question, well, what if it's never maintained, or, we're not gonna, people aren't gonna maintain it? Well, if it's never maintained, then it's just like you buried it behind the wall. Eventually it will foul up, performance will decrease. The difference is when you realize that, you pop it out, you brush it off, and you put it back in. You don't have to bring in a backhoe. Now, that's not what we recommend, but that's probably some real life examples of how it might function. The recommendation, though, is if you put them in a structure that structure is going to be inspected periodically. If you come through and they're draining water, then they're working. Now, if you have a rain event, they should be producing quite a bit of water. If you notice that that decreases or stops draining, pop it out, brush it off, and put it back in. Now, an official recommendation is to maintain your peak performance every 2 to 5 years, depending on the quality of the backfill. Good backfill, higher end, pop it out, brush it off, put it back in. But it's very simple and very quick. I'm going to talk a little bit about Michigan DOT and a project that we did with them. We partnered with the Michigan DOT, TSP2, an engineering firm, independent firm who did evaluations over 2 years. But the project was to go into a box culvert that had historically had problems with drainage. The soil filtration component had failed. They lost a lot of backfill. They had to come in and repair a bunch of voids and sinkholes. Then they plugged all the weep holes. Well, of course, then over the years, pressure built up, caused cracks. They were losing soil fines. So the project was then to go through and restore drainage to this 172-foot box culvert, double twin barrel. So this is just a picture of the coring. They recored the weep holes to put in 4-inch weep holes. And I'm going to show a video of the Michigan DOT maintenance crew. It took them about 8 minutes per unit, but I've cut it down to about a minute, so you can just see the highlights. But this is them explaining how they go through and do installation of these units.
All right, initially when we pull the core, you never know what you're really going to get right away, but normally there's a lot of dry sand. Makes the filter hard to push in at first. So we'll pull the core, let it drain, and then once it starts getting to be kind of watery, kind of lubricates the filter as you put it in the wall. It's easier to seat up against the wall. Now this one's wet right off the bat, so this one will go right in. And once it's seated up against the wall kind of tight, Tim checks the bottom, make sure we're making contact. Then we'll start drilling pilot holes for lag screws. I don't initially torque the lag screws down tight right away. And then I'll just go around again and tighten them until it feels like the screws are tied up against the washers, where the washers won't spin.
So that was the Michigan DOT maintenance crew from the Grand region, which is on the west side of Michigan. So there's a lot of sand in this area. So even though the original backfill had washed out, they did have, what they considered like a class 2 sand, just native soils that they were able to put the units into. And that's very typical in that area of Michigan. So they, when they went through, and this is the box culvert I was mentioning with the change in vegetation, which can tell you how long the structure had been suffering from high water content. So this is the one they had plugged the weep holes, and then they started getting new cracks. Water was coming out of existing settlement cracks, and soil fines were passing through those new cracks. Within 48 hours of installing the units, even though there had been significant rain events, the cracks, now these were not large cracks, the settlement cracks were, a little bit, but they still were not significant cracks, but they were all dry and no more water was coming out of the cracks. Their water was flowing freely out of the units. So the engineer spent 2 years, went back, first 48 hours, then a week, then a month, 2 months, 4 months, 6 months, etc. And then each time removed a few of the cartridges and did an evaluation on them. And all of his reports are posted on the TSP2 website. If anybody's interested, we can shoot you a link. But one of the things that was tested was 5 different geotextile filter fabrics. And these samples here were taken right after the unit was put into the wall, screwed down, the engineer took water samples. And these are samples from 5 different geotextile filter fabrics. And it looks like, wow, this geotextile filter fabric is really working and this one is not working. Well, what the engineer had determined is that this was a result of the initial blush that was caused by how much the backfill was disturbed during installation. Because when he came back a week later, all of the filter fabrics were flowing and none of them were passing any soil fines. And this phenomenon continued for the entire 2 years, with one exception. One of the geotextile filter fabrics was a woven fabric, and the rest were non-woven fabrics. The woven fabric was not able to stand up to any type of cleaning, and this was known before we went into this test. It's just not strong enough. So our products come with woven geotextiles, which can fit all of the different soil types that you may be having in your situation. So the engineer also, as I mentioned, he inspected the units. He took some out that had been in for a month. Some had been in for a few months. Some had been in for the entire 2 years. And when he pulled them out, it looks like this is, maybe this is clogged, but this is actually the filter cake or the transition zone that establishes itself on top of the geotextile filter fabric. And because it was permeable, the geotextile filter fabric was flowing fine and did not need to be maintained, even though he took them out at the appointed time for that location. Here's a photo of one that had a backflow prevention valve on it, and this measured the amount of withheld water pressure that was required in order to open the valve. So there's a little bit more pressure required, of course, because it has to push the valve open, but it was not a significant increase in the pressure on the wall. They had a little bit of issues with this iron ochre, but it was not significant. So every time it rained, it all got flushed out and did not foul up the filter cartridges. If it had, the filter cartridge could be replaced. And then they were able to tell that the geotextile filter fabric was not clogged simply by holding it up to the light, to a flashlight, and seeing through the filter fabric. I want to talk a little bit about some test data because, there are no ASTM standards or AASHTO standards for a weep hole and nothing for a maintainable weep hole. So we've had to have a few different organizations perform some tests on the products. I'm going to quickly walk through 3 of those. The University of Missouri designed a whole bunch of, these large boxes. They were like 12, 13 feet long, 6 feet tall, 8 feet wide, 7.5 feet wide. And they put in different backfill material. They put in tensometers and pensometers, and then they put in a constant head. And what they were able to observe is that just about a couple feet before the unit, the water pressure dropped. so that by the time the water got to the unit, the pressure at the wall was 0. And then they were able to measure that further out, the water pressure increased, so that they were able to model that if units, and this is a 4-inch unit, if units are spaced 5 to 10 feet apart in this scenario, they will maintain 0 pressure at the unit, but there will be pressure between the units. And if you go past 10 feet, pressure will increase at the unit. So the pressure will not, all the water will not be draining out at the unit. Now, they did this with different kinds of backfill. So they were able to model some clay versus sand to come up with their observations. And then they were also able to model an increase versus they tested with a 2-dimensional weep hole and a 3-dimensional weep hole. And they were able to model the performance increase. Now, I bring this up, and I'm showing just a real quick image here about the least drawdown and highest pressure is in the middle of the units. And this is important when considering an application, especially a concrete application. You would think the middle of the unit is the panel is the strongest point. The seams are the weakest point. So placing units near a seam or near a crack, never on a seam or on a crack, will make sure that the lowest pressure is at the weakest point and the highest pressure is at the middle of the panel, which is the strongest point. TR Environmental did built a massive piece of test equipment here, where they were able to pass water, cycle water, pump it in, put it through a pipe, measure different PSI, and measure the different performance of different geotextile filter fabrics and different types of configurations of weep hole filters. They were able to then actually measure the increase in the flow rate of a 2-dimensional versus a three-dimensional conical shape. Finally, I'm happy to announce that coming soon will be an ASTM standard. This is from the GSI Geosynthetics Institute. This gentleman here, Robert Corner, you may have studied some of his or his father's geosynthetic textbooks in college. He was the one who wrote the standard originally, and he's updating it to include test apparatus for clogging of conical shape weep hole filters. So he created some apparatus here, used stone or pea gravel and an impermeable sand in order to measure clogging effect of the conical shape. And that has gone through committee. It is hopefully going to be voted on soon by the entire committee. So out of some of these things, I'm just mentioning 2 states. There are many other states, but Michigan DOT and Arkansas DOT have taken the lead on starting to precast weep holes into their new box culvert sections, so that when they're delivered, they will be able to just insert the units into the precast PVC sleeve. Greg, if you're on the phone, can you give a quick update as to some of the counties and what they're doing?
Well, there were a couple of counties, well, no, one county in the UP or Upper Peninsula of Michigan. They did a precast box culvert. I think they did 2 of them up there. So much like MDOT did here, in some of the areas of Grand area and a couple others. Now, Arkansas DOT actually has done more than 2 now, so we'll have to get back to them and find out how many. They just got some other product for it.
And what can you tell us about Dickinson County and what they've done? I know it's not
Okay, well, Dickinson County had 6 roads that were going over creeks. This is an area in the Upper Peninsula that has a whole lot of traffic from logging. And as David had said before, soil can be disturbed with the heavy trucks on the road. And they had been losing soil and dropped down the approach 8 inches from the box culvert. The approach of the road dropped 8 inches. I'm not sure if this is from the trucks or just water coming out of the existing weep holes and bringing the soil with it. Their solution, just like MDOT had done at one time, is to use concrete and fill in the weep holes and hope that the wall lasts. But they recognize the jet filters, and now they've got 4 of those projects done, and they've got 2 more to go. This is a very good example of keeping the soil out, but letting the water through, and stopping the voids up above.
All right, thanks, Greg. I'm going to switch now and just bring in a few different project applications and examples. I'll be done in a couple of minutes, and then we've got time for some Q&A. First, I want to just bring up we do a lot with seawalls, and I know you probably, none of you are, I don't know if any of you are doing seawalls. And I bring this up not because it's a seawall, but because this is an example of new construction where the weep hole filters had been specified based on a certain type of backfill that the engineer had, put into the design. Well, for whatever reason, the backfill that was actually used was not the specified backfill. And they didn't realize that until construction was done, and the units weren't performing as they had thought they should perform. So after investigating, they realized that, whoa, it's the wrong backfill. Now, if this had been buried behind the wall, there's nothing that could be done without major expense. The flexibility here allowed for the cartridge to be popped out and a different cartridge to be put in with a different geotextile filter fabric that better aligned with what they ended up with their backfill. So the products can be very flexible. It's not something we do very often, is replacing filters, because they're designed to be maintained, but it can be if needed. Illinois DOT is probably the leader in retaining walls, use of the product in retaining walls. This is an example that one of the pictures I showed earlier showed a wall rotating. Well, they noticed this stretch here of retaining walls and the wing walls, this abutment. 4 60-foot panels had suddenly started to rotate after decades of stability. And then as they were watching them, one of these fell over during a polar vortex. And when they excavated, they realized that the stem and the base had totally corroded away. So the only thing holding this panel up was the weight of the panel and the surrounding soils. Now, all of their, many of their, the roadways in Chicago are below grade. So these panels are all over the place. They were all built approximately the same time. So they think that a lot of them may have a similar issue. So they have gone through a number of walls and put units into as an insurance program. I guess so what I would call it, I don't know if they label it the same way. But that one panel just to replace the 60-foot panel cost $400,000 versus about $4,000 to ensure that the panel would never fall over. And I didn't talk about cost earlier, but I should have mentioned that the Michigan DOT twin box culvert installation cost slightly over $20,000 to restore the drainage of 172-foot twin barrel box culvert. So Illinois also now uses them in new construction. They also have a special provision, statewide provision for them. We do work with MSE walls. Indiana DOT has a number of walls that were all built around the same time, 29 years ago, and they all have the exact same failure point. So they're going through and fixing the walls, sealing up the joints where they were getting the soil fines passing, and then putting units in order to drain the water out. New York DOT is also, they just finished last year, they finished a pilot where they put the units into a wall, and you'll notice the texture on the wall. And there's a gasket on these units that needs to seal up against a wall. So they ground down a flat surface so that they could install the units, and now are considering using them in other projects. Here's just a picture of what it looks like. Sometimes these units are inset. Sometimes they just need to be a smooth surface in order to seal. I'm jumping back to seawalls, but this is for a different reason. We do a lot of projects that are post-hurricane projects where hurricanes have damaged structures or caused other issues. And Hurricane Florence came right over Wrightsville Beach Marina a few years ago. And the marina reported back that when they got back to the property, all the units were draining, even though they'd been installed about 6 or 7 years earlier, and they had no damage or no water on their property. And that gets back to what we refer to as speed to drain. You know, a lot of times weep holes are just weeping, but when there's a rain event, they need to get water off from behind the structure quickly. Harbor Cove is another example where the Hurricane Ian came right over their development, and they had put the units in a few years earlier. And while other areas, other seawalls around them had failed because the water pressure was too great for their seawalls, they reported back that all of theirs were functioning. They had no damage.
David, this
we
is
do
Jason. I wanted to
Yes?
make sure we save some time for questions.
Yep, I just have 2 more.
Okay.
They can go into slopes. They just go perpendicular into the slope. As Jason, USDA and the NRCS and Army Corps all use them. We do have different specifications from different states. Jason mentioned the Michigan one. We can help out with that. I just want to give a real quick cost scenario. If you have a 100-foot wall, and let's say you put in units that are 6 feet apart, you need 16 units. The product cost to do that project is less than $5,000. Now, there's maybe coring, there may need to be some other things done, but from a cost point of view, it's a very minimal investment. And just show some pictures. The products have been used in many states by many agencies in those states, by private companies or private property owners. And last, here's my contact information again. I'll leave this up, and you can contact me if you need further information. All right, Jason, I'm done.
Thank you very much, David. Does anyone have any questions for David?
I got one comment about a certificate. I'm happy to do that. I'm sorry, was somebody ask a question?
This is Greg. I guess I just want to say I'm happy to see some West Coast names or DOTs.
I do think we have someone else that would like to ask a question. Is your audio working? If not, if you can't get your audio to work, apologies. Please type it in the chat box, and we'll be happy to get it to David. Does anyone else have any questions?
All right. Well, I am happy to if anybody has questions they'd like to take offline, please reach out to me. I'm also happy to, if you think this might be good for other people in your organization, I'm happy to do the same presentation or customize it based on whether it's engineers or maintenance crews or whomever the audience is. Just let me know.
I just wanted to add that maintenance crews at the Michigan DOT have been using this for about 12 years now, I want to say. So we like it a lot. And like I said, if you want to, I put my email address in the chat. If anyone wants to email me, I can send you the specification I wrote while at Michigan DOT for utilizing these in construction projects. And it does look like we have.
I've got one question I'm answering.
Yes, I see that. Yep.
So the question for everybody is, can the system be used for sealing cracks? The short answer is no, they don't seal the crack per se. They will reduce the pressure on the crack so you won't have the same amount of water coming through. If it's a small crack, then if you've relieved the pressure, you don't need to do anything with the crack from a drainage point of view. If it is a large crack, you still, I would recommend that you seal it up with a sealant. There's many different products you could use, but basically sealing it up.
Yeah, in Michigan, we'll do epoxy crack injection for something like that after we've installed the weep holes and drew down the water pressure. All right. Well, I thank everyone for their time. It is 1 o'clock and wanted to be respectful of everyone's time. So, Nancy, do you have anything else to say?
I did not. Thank you, Jason, for stepping up and taking control of the meeting. And thank you, David, for the presentation. It was informative and it is recorded, and I will stop the recording now.